Hey everyone, in this video we are going to practice another example of solute potential, only this time the graph does not have the line of best fit for you. You have to create the line of best fit. So we're going to show you how to do that in this video. So the background information is that a student placed various brined olives into beakers with increasing salt concentration at 26.8 degrees Celsius. Sodium chloride has an ionization constant of 2, and the data were collected and graphed below. So in this background information, they give you the temperature of the solution, and they give you the ionization constant of sodium chloride, because you are not expected to memorize the ionization constants. And since this was not sucrose, the FRQ gave you that information. Now, in order to graph the results of the data, we are going to need to calculate the percent change of the olives in the various different solutions. To calculate the percent change, we are going to do the final mass minus the initial mass divided by the initial mass times 100. Keeping in mind that some of these values will probably come out to be negative if the final mass is smaller than the initial mass. So for this first percent change, I'm going to take the final mass, subtract it from the initial mass, divide it by the initial mass, and multiply it by 100. And when I do that, I get 35.9%. I'm going to do the second thing with the next molarity at 0.1. So I'm going to take the final mass minus the initial mass, divide it by the initial mass, and multiply it by 100. And when I do that, I get 23.6%. I'm now going to fill out the rest of the table by doing the same calculations to calculate the percent change of the olives in each of the different solutions. So here are the rest of my values on the table, and pay attention to where the values become negative. Once it becomes negative, this is indicating that the olives are losing water. That is why they have that negative change in mass, is because water is now flowing from the inside of the olive to the outside solution. So when we graph the results of this data, we are going to need a y-axis that accounts for some of the values which are positive and some of the values which are negative. I'm going to do that now. So I've labeled my y-axis as the percent change in mass of the olives, and I've made sure to leave enough space to have 0, as well as the negative values that I'm going to need, and the positive values as well. So this part up here represents a gain of water in the olives. These numbers down here represent the loss of water for the olives. Now I'm going to add my x-axis, which is the concentration of the solutions. So I've added the concentrations. This is a molarity of the substances. And some students don't like putting the name of the axis here in the middle of the graph. If you want to put the name down here, that would be totally acceptable and fine as well. So now that I have both of my graphs labeled, what I'm going to do is I'm going to draw points on this graph for each of the different concentrations. So for 0, I'm going to come up here to the 35.9 mark. So here's my 30. And the way that I scaled mine, each of these is worth 2 units. So this would be 32, 34, 36, 38, 40. So I need to go pretty much to the 36 line. So 2, 4, 6. So about right here. And I'm going to place a dot. Next, I'm going to put a dot at the change in mass for the 0.1% concentration. And so that change was 23.6. So I'm going to come over here. Here's my 20 mark. Here's 22, 24. So it's going to be somewhere in between. Now I'm going to go to the 0.3 mark, and I'm going to put my dot at 10.9. At 0.5, I'll put the dot at 9.4. For 0.7, it'll be at 6.2. For 0.9, it'll be at negative 9.9. And for 1 molar, it'll be at negative 11.7. So now that you have put dots at each of the different concentrations, What we're going to do now is do a line of best fit. So the line of best fit is basically a line that will go between as many of the points as possible. And this is where it gets to be a little bit challenging, and because of how you draw this line. So you may draw your line slightly different than mine, and that's okay. And I'm going to show you how to make sure that the reader knows what your intended x-intercept is, because that is what we're looking for. We're looking for what concentration did these olives neither gain weight, in other words, positive change, nor did they lose weight, which would be a negative change. So none of these dots actually cross at this line right here, which is a 0% change. So we need to figure out what it is using that line of best fit. So as you can see from my line, it doesn't necessarily hit every single point. It does try to get close to many of these, but the reality is I could have drawn this line slightly different, maybe a little bit closer this way, maybe a little bit closer the other way, to at least go through one of these intersects. So when you have to draw this line by hand, the values that you're going to use are going to be much more generous and much more flexible than if the line is already drawn for you. So once you have your line of best fit, what you're going to do is find your x-intercept. You're going to find the concentration at which the cells, or whatever it is you're studying, did not gain weight, nor did they lose weight. They had a 0% change in weight. And so that value is going to be about right here. Now I need to figure out what that value is. So halfway between 0.7 and 0.9 would be 0.8, which is about right here on my graph. And I can see that my line, my intercept, does not quite get to that point right there. It is slightly before. So halfway between 0.7 and 0.8 would be about 0.5, which is what looks like where my line is intercepting. So the concentration at which there would be no loss or gain of water would be at about 0.75. And we need that concentration to be able to calculate the water potential. And we need this information to be able to calculate the water potential of the olives. So when we're calculating water potential, it's the same as calculating the solute potential. The formula on your formula sheet gives you that helpful reminder that for open cells, that the water potential is going to be equal directly to the solute potential because the pressure potential is 0. And so all we need to do is calculate the solute potential and we'll know the water potential. And that's the formula for calculating the solute potential. Now keep in mind that you are given this, you're given this, and you're given this. The tricky part for these calculations is remembering that the C you need to use is the concentration where the line of best fit crosses the 0, where there's no net change in the cell itself. So in our graph, or at least on my graph, based on how I drew that line of best fit, my concentration I got was about 0.75. So what I'm going to do now is I'm going to insert all the variables, or replace all the variables with the numbers based on what I was given. So we were given the ionization constant in the background information. C is the concentration at which the line of best fit crosses the 0. R is our constant given on our formula sheet. And the temperature must be converted to Kelvin, which is why we add 273. So when I plug these in the calculator, I get negative 37.3 bars. Don't forget that there is a negative sign in this equation, so please don't forget to add the negative on your answer. Thanks so much for watching. I hope this video was helpful. Bye.